It's fine. So, yeah, I wanted to talk about, I think so, maybe other than the LIGO talk, this will be one of the few talks involving stuff and not pure thought. So, anyway, so I want to start, first of all, saying congratulations to the Institute for the Center for completing 10 years. I actually came to know Spenta only a few years ago. He serves as a member of the Infosys Science Prize in physical sciences, and he's a member. He's extremely energetic, he's broad-minded, and I can say that he has very good choice in a very good taste in choosing people. So I'm pretty sure the institute will have a center will have a great future. Okay, so I wanted to start with an observation, which is there are some subjects, astronomy, biology, geology, and the new subject of exoplanetology, which are phenomenological subjects. Okay, what do I mean by that? Phenomenological subjects are, the main focus is, there's usually a lot of diversity, and you don't try to understand all the specific details. If you want to understand the specific details of the architecture of the solar system, it'll always be some accident. Maybe when the protoplanetary disk was being formed, we had a star come by, and it influenced the architecture of the solar system. So in phenomenological subjects, the point is to become an explorer and to find all possible ecological niches. Okay, so in the universe, all kinds of objects exist unless they're absolutely forbidden by basic laws of physics. And the job of the astronomer is to go and find the occupation indices of the phase space. In contrast, physics is exactly the opposite. It's actually distilling the vast phenomena into as fewer numbers as possible, or a few equations as possible. That's why astronomers I understand, physicists I understand. I never understand astrophysicists because they usually tend to know neither, in my opinion. Okay, well, so in phenomenological subjects, there are three distinct steps. One is discovery. You've got to go find the stuff. The idea that I'm able to figure out things on my own, it's actually simply wrong, simply not true. The universe turns out to be much, much richer. It had 13 billion years to play around and make things. Most of us only have maybe 13 years at most to imagine things of this sort. So we're off by a factor of 1 billion. Okay, so you must go and go discover stuff. Then the next one is, once you discover, you have to really, that's when the phenomenology starts. You have to really observe a lot. You have to do surveys, catalogs, time series to find patterns. And once you find patterns, that's when the physics begins, is you come up with inference, which is physical models to explain the observations. And occasionally, the physical model is so dramatically successful, unreasonably successful, that to me is astonishing, actually, that you can actually use the physical model to make a prediction, which sometimes turns out to be true. To me, this is the most unreasonable part of of how the universe is, that we can sit around and actually make some more physical models and anticipate future findings. In my view, it's very simple. Discovery is largely a function of technology. I would say, flat out, I would simply say that I know of no such super smart person that by sheer thought they would go and make discoveries. It's purely a function of technology. Occasionally, someone may be brilliant. Usually, someone is usually more lucky than being brilliant. Okay, so I know I made some statements here that are, let's say rather strong. They're true, that's all. What else can I say? But this is a good audience, because one of the things I've learned by interacting with theorists whom I do like, as many of my theorist friends know, that I'm a very big fan of them. And even written papers with a few of them. The better the theorist, the more they like humor, actually. That's what I found. And after spending time with Spenta, I found that the string theorists are the best. They really do like good jokes. And the mark of a good string theorist is the more you appreciate jokes, the better string theorist you are. So I had to go really out of my way to come up with a few jokes on the occasion of 10th anniversary of ICTS. Okay, so we'll come back to that theme a little later. So discovery is a very big phenomenon. There are lots of things. We can go discover the universe, we can go discover exoplanets, but I want to talk of a specific area in astronomy, which I would say is the rise of time domain astronomy. I think the time domain astronomy has been bubbling along. It's now in it's the full ascendant mode. I would say another maybe 5 years, we'll see the peak of time domain astronomy. And it's a good thing to, in astronomy or any phenomenology subjects, when you have powerful machines or methodologies that come on, the first 5-10 years are exciting because you can just go, turn on the machine, and discoveries happen. You don't have to be bright at all. If you build a big enough telescope, you will actually make great discoveries without trying hard because you're using nature to make those discoveries. So the main topic I want to say is this general methodology will be a very big part of astronomy in the next 10 years. In the same way that exoplanetology began, let's say, approximately about 20 years ago. And it's now in full swing. It's probably at its peak at this point. But then, there's such a large area, time domain astronomy. We'll focus on something of some interest to this conference and of somewhat timely value to the great progress in gravitational wave astronomy by focusing on the buildup of elements in the universe. So this is how it all began, as you know. Let's see. Okay, so we have the small fluctuations in the universe. It's astonishing to me. These fluctuations are only 1 part in 10 to the 5 different from one part of the universe to another in both matter and energy. But again, given long enough time on the universe, these fluctuations actually are thanks to gravity, they grow, and you get structure formation, and within that, you get stars that are condensing, galaxies being put together, galaxies merging, all this fun stuff that really happens here. Okay, so the universe was homogeneous in energy and matter to some astonishing degree, and but it's also very simple. When the universe began, there's only hydrogen and helium. Okay, that's it. A little bit of lithium, thank God for that, for some people I know. It's a joke. Okay, so some of you think the 2 most common elements are hydrogen and stupidity, but that's okay because helium is a gas which is second synonymous for stupidity in some ways. Anyway, the rest of the periodic table is absent, and so the universe was simple chemically also, not just structurally. Okay, so there are 2 parts. I would say there are 2 big developments in the 30s and a bit late in the 50s. 30s was, of course, an understanding of how stars work. The whole fusion reaction that goes hydrogen, helium, carbon, leaving carbon, oxygen, white dwarfs, that was all understood by end of 30s, work by Hans Bethe and others. And the other one was how to form elements which are beyond the light elements. Okay, and I'll come to that. And it has 2 parts. One is the observational part, and that's, I would say, beginning of time domain astronomy began with Fritz Zwicky. Zwicky was the first astrophysicist employed at Caltech for the 200-inch project. Then he really got into astronomy in a big way. I think he ended his career as perhaps one of the greatest astronomers. Here he is. He's actually observing. He was remarkable. I do astronomy, but not the Zwicky style, because this guy used to observe on his own, develop the plates in the afternoon, blink the plates, find supernovae, and then write papers with a little theory in it. That's really remarkable. Anyway, I consider him to be the most outstanding astronomer of the last century. Well, of 3 people in the US, he was certainly the most outstanding one. So I always measure people by Zwicky units, mostly micro Zwickies, but once in a while I do see a milli or a centi Zwicky. Then it turned out that I was wrong, that this is already a copyright thing, that von Karman was a professor at Caltech, very famous, as you know. He also had already coined the Zwicky unit, and it's used as a unit of roughness. One Zwicky is an amazing amount of roughness, okay? So both these are correct units, actually. Okay, so the other one is the understanding, the nucleosynthesis and nuclear astrophysics that began, and many astronomers should know what is B squared FH paper, which led to our understanding of how we went from the simple periodic table through stars and supernovae as time went on. Okay, so here we are all stardust. So here it is with the hydrogen, helium. There's a bit that cosmic rays produce. These are fragile elements. The small and large small stars, as they, like the sun, it's going to end as a carbon-oxygen white dwarf. So it's going to spew out maybe about 0.4 solar masses of stuff, including carbon and nitrogen and oxygen when it dies. And you can go along to more massive stars, but once you get to higher Z elements, you do need supernovae. And a supernova is simply when a star dies, and there are basically two types of supernovae. One are core collapse supernovae. These are massive stars, and the core is massive enough that eventually nuclear fusion, as you go all the way to iron, can no longer keep up the pressure gradients needed for mechanical balance, and therefore there's a total collapse. Gravity wins in the end. Gravity always wins in the end. And then there's thermonuclear supernovae, which are really very strange objects. You couldn't have predicted that. That, to me, is an excellent example of something you couldn't have predicted. Only after discovery you could understand this. Okay, so iron is very, very special because it's easy to, that's the end of your thermonuclear reactions, because iron, as you know, is the most tightly bound nucleus, so you can't go beyond that by any sort of fusion reactions, and that's why you have fission and fusion reactions, and iron is, in fact, the nice dividing line. Okay, if you want to go beyond that, we now know that perhaps the R process elements, or the the precious elements, are actually made in these neutron star coalescences. They really are precious because in order to get your gold and platinum, the spore star had to die twice. Can you imagine? I mean, in some sense, they're the most horrible elements because they're coming from not just one stellar depth, but two. I find this, again, very astonishing that our universe, we make these things in a way that you could have just figured out from first principles. So it's all in details here. Okay, so I hope I've given you a broad idea, time domain astronomy, nuclear synthesis. Now let's get on to how do you make these things happen. It's all right to sit around and talk about ideas. In the end, you have to go and make things happen. That, to me, is very, very important. And you also have to make it happen in a reasonable time scale. Anyway, so about maybe 10 years ago, about 11, maybe 12 years ago, actually, I started thinking, I was working on gamma ray bursts, and the SWIFT mission was launched, and I said, well, there's not, I don't like to work in a field where there are too many other people working, for the simple reason, if the other people working in the field, many of them, then you have to be brighter than them and work harder than them to contribute. I don't like to work hard, and I'm not brighter. Okay, I keep telling this to Ramesh, he doesn't believe that. So whenever there are too many people, that's the time to leave, and best is to go and do something else, and to preferably be in a field where you can create it so that you don't have a competition. Anyway, so I decided, as usual, to get into this, so I taught a course on high energy astrophysics, and I decided, okay, the thing here is to go and have a factory, is to change the way we're looking at supernovae as an industrial approach. No longer a grad student and a postdoc or a faculty member observing, just doing what Zwicky did, but slightly more upgraded, but to actually completely change to an industrial astronomy, which means to get the astronomers out of the loop. It'll all be done by machines. And that's what's the Palomar Transient factory. And the concept of factory is use the 48-inch telescope, which is very special for its wide field imaging, make it a discovery engine, take images, difference them, find new stuff, all real-time pipelines, confirm them because there are systematic artifacts with a 60-inch, and then evaluate its context, see if it's something special, get its classification to 200-inch. And fortunately, this could be done because these 3 telescopes are run by one management, and I happen to be the director. So we went from the concept to first light in 26 months on this integrated approach. People talk of hardware, which is important. Software, of course, we all appreciate. But there's a new thing which I've coined. It's called Grayware. And the thing is, you want to make projects of this sort. There's tremendous amount of software for sure, but there's also algorithms. So I just ran around the world. I can say, basically, I looked for young people. I said, OK, come and work with me. I'll make you rich and famous. I certainly made them famous. Rich, maybe we have to wait. But anyway, so there are all these new things we brought in. Machine learning, led by Josh Bloom, now a professor at Berkeley. All these were postdocs. Nick Law was a postdoc who had just finished something. All right, it doesn't matter what they're. If they're bright, I evaluated and said, OK, come and work with me. You're the project scientist. So I have this style, which is to get young people right after their PhD, give them big jobs, and tell them, we don't have meetings. End of the year, things have to be done. Otherwise, it's their life on stake, not mine, because if they make a mistake, it's a 100% effect. For me, it's only a 1% effect. So all this stuff worked very, very well. And that's how in 26 months, we had this completely robotic, highly redundant pipeline system that could do real-time analysis. OK, so here's where phase space, the term was introduced by Zwicky. Well, not in the term phase space, but in his book on morphological methodology. But I'll call it the Zwicky diagram. The time scale, 1 day, 100 days, 1 year, and the peak luminosity, which is how bright they are in magnitude units. And the reason astronomers use magnitude is very, very simple. They're a little strange. They're like minus, more minus, brighter it is, and log, and all this sort of stuff. Frankly, I think many astronomers are worried. Physicists are pretty bright guys. They know a few things, but they know them very well. So by using magnitudes, it usually gets most of them, kind of away, so we can actually continue doing more fun stuff, which is why they end up working on uninteresting problems. But OK, so here's classical novae, thermonuclear supernova and core collapse. The big difference between physicists and astronomers, a physicist will immediately say there are three families, there's some physical principle, which is all true, but they're missing the point. When you see a diagram like this, if you're an astronomer, if you're an explorer, you should say, what can I do to go and discover new stuff? If you haven't thought of that, you're not an astronomer. OK, it turns out that's what machines do. If you build stuff, now we have stuff. There's things beyond this. It's not just PTF that the project I began. There's Pan-STARRS, which was a contributed a lot, Assassin, now Atlas, many other projects. So there's stuff all over here. You couldn't have predicted this from first principles. OK, so you have some supernovae that only produce calcium. Remarkable. The calcium in your bones and teeth come from one kind of supernovae. The iron in your blood comes from another kind. And here we are, all together. I'm not religious, but it's almost could make you religious. OK, luminous red novae. Well, there are 2 types. Perhaps stellar merger, electron captured supernovae. We don't even know what these are. I'm not even sure the name is right. Superluminous supernovae. These were only thought, even 10 years ago, to come at the early universe. We can find them next door. OK, so one of the things we did after doing this grand exploration, we said, OK, let's increase the cadence. OK, so this is the idea, is to understand all these details of pipelines and say, how do I decrease the latency in these things? And we found a supernova within 10 hours of explosion. It's a young supernova. And for reasons I won't go in, this is a 1A supernova. We could say that this actually comes from the coalescence of 2 white dwarfs. And these events will be very much seen by, the coalescence part, just like LIGO today by LISA tomorrow. OK, or 10 years or 15 years from now. In another case, in thesis student of YISA, we found an example where what's called a single degenerate model. Here's a white dwarf. Another star is transferring matter. White dwarf increases mass, Chandrasekhar limit. Boom, it explodes. That's the general idea. So nature makes 1A both possible ways, and maybe the other ways too. So these sort of things that people set up in a very physicist approach, you say, is this either A or B? And you think you're brilliant by actually sharpening the question. It's a silly approach. It's always A plus B, and then there's a C plus D you don't even know. Okay, and your job is to find what is the ratio of A to B. That's all there is to it. A is never 0, B is not 0. Okay, so after that, we said, okay, we should get ready for LIGO. So can we do searches in wide fields? These are very hard technical problems, so most of you don't understand this sort of stuff or think about it. You may think this is all easy. This is very, very high-tech problems, okay? Because once you do 100 square degrees, you can generate about something like 10 to the 5 candidates, and then you have to have all that stuff sorted out in an hour, and then organize automated response to telescopes elsewhere and in space. And it has to be with some fidelity. You can't ask Hubble to slew and then say, well, you know, I made a mistake. Okay, so, well, we did that. We are able to now go to 70 square degrees and find gamma ray bursts. And in fact, we did even better. We found untriggered GRBs. That is, we found the optical afterglow of a GRB even before being told that gamma rays came from this, because the Earthbound missions were occulted by this source, but it was found, the gamma ray burst was detected by a Russian mission, and there was a 2-day delay in the download from Mars. And we told them before the data came, there's a gamma ray burst, this piece of sky, approximately this time. Okay, and I do want you to appreciate there's all this stuff happening in a lot of very software. And look at all this triggering that's going on. Keck, Swift in Hawaii, Swift in space. And in the end, we have a nice result. Okay, so why stop here? Why don't we automate the whole discovery process? So to me, this is a big fun thing is, can I build a machine that will make discoveries without the astronomer in the loop? This is a hard one, but it's at least I'm on phase 1, which is to get the machine going. And this is the Zwicky Transient facility. You might have been surprised, Zwicky, if you really bought the idea he was the greatest US astronomer of last century, I know he'll never get a mission named after him because of the other part of Zwicky and the roughness unit. All sorts of other lesser people have been named with missions. I mean, significantly lesser people, I mean. So I thought, okay, I'll at least pay homage to this person. And it's got a whole worldwide thing, these sorts of projects. You really need not just the money, you also need very smart people. Okay, so the ZTF camera is very large. It's 47 square degrees. The other cameras here, of course, they're behind bigger telescopes, so it's not a fair comparison. And I won't go into this, but the main focus here is to do wide, shallow surveys, because the focus here is to go after bright events, because that's where discoveries are most easily made. Okay, so it's a beautiful, this is the world's largest compact camera. Let me explain. The sensor size of this is 1,100 square centimeters. It's about half that of LSST, okay, which is $1 billion total capital project, capital plus ops. And the volume is 1/25th that of LSST. So when I say large compact, I hope you understand. This is a marvel, actually. We achieved first light. I'll show us an image. In order to complete, so it's one thing. Many people say, okay, we'll go find supernovae. It's no big deal. There's a supernova in the universe once a second. By the time I've given this talk, that's, let's see, 20 minutes, 1,200 supernovae occurred. Okay, now, of course, mostly in the distant universe. So finding supernovae is not the big thing. You have to actually understand there has to be a plan, an end-to-end plan. What is it you want to do after you find things? So you need a follow-up, and you need a lot of new tools, and that's what we are now doing. So we've developed a tool, spectroscopy on demand. So the way much of the spectroscopy is done is, you convey that information to a colleague, data acquisition, you say, oh, here's a field, here's a slit, I'm going to put it in with little joysticks, or some variation of there. But we have now built a robotic, ultra-low resolution spectrograph itself. It's a novelty, which is called an integral field unit. So you simply slew the telescope. It has sufficient entrance aperture that within the pointing errors, you will get the spectrum. So it is robotic spectroscopy on demand. So we can go from photons hitting the CCD to getting the classification in something like 30 minutes. This is now increasing the turnaround time. Okay, so, and already it's had a great success. We found one of the most highly magnified gravitationally lensed supernova, one of the nearest tidal disruption event. So I hope you're convinced that by now that when you build these machines, and they're powerful. You don't have to work hard. Nature is so rich, the stuff starts falling on your lap. We have a robotic adaptive optics system. We have our own telescope, the Kit Peak 84-inch, kindly donated to us by NSF. And this is a project with IUCA and University of Hawaii. There's a lot of new stuff we're doing. It's called broker service. I don't have time to go into it. It's like you get all this data, then you have to do a lot of contextual analysis. What is it I'm looking for? So think of a world where there's so much data that if you don't have an idea, you'll just get data poisoned. You won't know what to do. So that is called brokering services. Is if I get a lot of data, how do I analyze it intelligently to actually pursue a specific project I have? So again, this is lots of very interesting interface between computer science and astronomy. Sentinels, we want to keep things on the sky, let us know if something has changed, sends a cell phone alert, then I can say, oh yeah, I should go and look at this because it's undergone a state change. Okay, so here's one of the examples from our new robotic spectrograph. It's a beautiful, we came to know because it's a 1A supernova, and we came to know it is much brighter than it should be, and you can see it's beautiful. This is actually the supernova. It's split. The supernova is a point source, so it's split into actually 4 point sources. The host galaxy is a ring because it's so perfectly aligned. The supernova behind redshift 0.4, host galaxy at 0.2. Okay, so you can see that not much work, great discovery, easy paper in science. Okay, we achieved first light, wrapping up. And next time you go out in the sky, please, tonight, you can take a look. You can see Orion easily from India. This is the Orion asterism, the hourglass part. Here's the belt. That's the size of a camera. You can visually see how big this camera is. And that's the actual image. Okay, so we're on. We'll start a survey in another month. And the ultimate celestial cinematography will begin with LSST in 2022. But I want to do all the easy stuff between now and 2022, so those guys will have to work very hard going after faint stuff. Thank you.
Everyone is overwhelmed.
Hello, thank you very much for nice talk. So my question is related to the astronomers' view of the classifying things. So we used to see supernovae as a one thing, and then we started dividing into 1, 2, and then 1A, 1B, C. And when people think from a theoretical point of view, we tend to see a continuum, or we tend to see it from the origin point of view. This I kind of find sometimes confusing that the 1A we see sometimes as a tightly bound group of objects, but from the theoretical point of view, there should be continuum, like from superluminous to superluminous to extra superluminous to normal luminous to underluminous. So what do you think about that? Like, I mean, does the theoretician point of view helps in
clearly you're obviously a physicist. Okay, I think your approach is wrong actually. What do you mean there should be continuity? Yes, supernova just stuff comes and goes down, and therefore it's one phenomenon. It's not true. The physics of 1A supernovae, the thermonuclear, is very different from core collapse. So why should you try to link them? Yeah, eventually it's all the 4 equations of basic physics.
May I suggest that you continue this over lunch because it's very technical.
Sure. Okay.
Are there any other questions?
Shri, I hadn't heard of this optical counterpart of the GRB that was discovered before the GRB was known.
Yeah.
That's fabulous. Now, people have always talked about these orphan afterglows, right?
Yeah.
Because the GRB is a very directional phenomenon, whereas the afterglow could be seen over much wider angle. So if this facility can now find all the orphan afterglows and identify them, I don't know if you can do it, so will you be able to, or has it already given an answer on
it's what good. Yeah, so absolutely. In fact, this is something I've been thought a lot. This is to do the optical, there are 2 types of afterglows that I think have yet to be discovered. One is the orphan, which should exist. There's no question, okay? This sort of level of theory is very robust. And so These are simply the geometrical part. Then the other kinds of afterglows, which I'd call as dirty fireballs. So there is no fundamental reason why the GRBs we see today should all, the new FNU should peak, let's say, between 50 keV and few MeV, or 20 keV and 50 MeV. Maybe there's some deep reason, but there's always a suspicion that the initial Lorentz factors don't have to be such that it peaks there. So these dirty fireballs, so these two projects are in fact exactly what I've been engaged with a grad student, Anna Ho. That's her thesis project. And to do this, you really need a very large field of view, and that's sort of so I think if ZTF discovers the orphan fine is fine. It's little confirmation. It's a couple of papers, and then we are done. Okay, but if you can find dirty fireballs, it'll be a whole new industry comparable to GRBs. And we have put some upper limits with PTF already. That is a rate of dirty fireballs does not exceed that of classical GRBs.
I think we should move on to the next talk.